Write an equation for the function shown. You may assume all intercepts and asymptotes are on integers. The blue dashed lines are the asymptotes. So this is the same techniques that are involved in graphing. We're just going in reverse. We're taking the graph and we are trying to build a function that has the different aspects of the graph. So the different things that are important when it comes to rational functions, and I know this is going to be a rational function because of these vertical asymptotes. That's the only type of function that we've seen so far that has vertical asymptotes. So we'll assume it's rational. Now, rational functions have some important things that we need to look out for. We need to look out for X-intercepts, Y-intercepts, horizontal asymptotes, and vertical asymptotes. Okay, so x-intercepts. This is just where a function crosses the x-axis. So I can clearly see an x-intercept right here. And the coordinates of this x-intercept are the points, is the point 1, 0. So I have an x-intercept at 1, 0. Y-intercepts is just where the graph crosses the y-axis. And in this case, the y-intercept is going to be 0, -1. Horizontal asymptotes, those are just horizontal lines dictating where the graph is going as we let x go to infinity. So this horizontal asymptote right here has the equation y = 0. And vertical asymptotes. Vertical asymptotes are places where division by 0 occurs. And we have two vertical asymptotes. We have one at x = -3 and x = +3. Now, to make a function that has all of these different aspects, what we need to do is just start off. We've already said it's rational, so I'm going to just throw in a division bar here. I'll start with the vertical asymptotes. Those are actually pretty easy. All we need to do is make these zeros that we have for the vertical asymptote locations, make them zeros of the denominator. So just change these into factors. So this would be x + 3 as a factor, and this one would be x - 3 as a factor. Just bring the constant term over with the x value, so adding 3 to both sides and subtracting 3. All right, so that takes care of our vertical asymptotes. The x-intercepts, these are zeros of the numerator. So if I have a 0 at 1, then I need to change that into a factor and make it x - 1. Now, the horizontal asymptote should just take care of itself. And if you'll notice, having a horizontal asymptote at 0, the rules of horizontal asymptotes are that if you have a horizontal asymptote at 0, then what occurs is you have the degree of the numerator less than the degree of the denominator. And that is the case here. I have degree 1 in the numerator and degree 2 polynomial in the denominator. So we're all set there. So we're done with 3 out of the 4 pieces here. Now it just comes down to the y-intercept. So I need a y-intercept at 0, -1. So in order to make that happen, there's generally going to be some sort of constant multiplier outside of my function here. And I just need to take the knowledge of the location of this y-intercept and solve for that, and that's going to place it where it needs to go. So for instance, the x value of any y-intercept is 0. So if I say, I'll just switch to a different color to solve. So f of 0 would be a times 0 - 1 over 0 + 3 times 0 - 3. And f of 0 is -1. So I have this equal to -1. All right, so that means in the numerator I've got 0 minus 1 is negative 1, so negative a in the numerator, and then 3 times negative 3, so that's negative 9 in the denominator. And I apologize if my a looks like a 9. All right, so there we are. So now this is the equation I'm working with. All right, so solving for a, I have negative a equals positive 9 because I multiply the negative 9 over, but then divide through by negative 1, so a equals negative 9. So that means my finished up and polished function is going to be f of x equals negative 9 times x minus 1 all over x plus 3 times x minus 3. And you could multiply that out if you wanted, or if you wanted to leave it in factored form, that's fine as well.